Hi, everybody. Today's lecture will be on Zoom, and the topic of today is antenna arrays. All right, so here's the agenda for the day. I will begin with some introductory slides on phased arrays, and only then we will get into the mathematical details. And today we will discuss only linear antenna arrays, so line of antenna elements. I will begin with the simplest case of an array composed of two components, two-element array, and then we will consider the general n-element array case, and we will discuss specifically the array factor, which will give us the properties of the radiation pattern of the array. And then if we have time, we will discuss several types of linear arrays. Okay. So first thing first, antenna arrays, what are they good for? So the main idea of stacking an array of antennas is to achieve control over the radiation properties without actually changing the individual elements. So which properties can we control? For example, we can improve the gain, the directionality of the array, or achieve narrower beam width, increase the radiation intensity, and also achieve active control. So we can basically change, for example, the direction of maximum radiation from one side to another in real time. So all these things can be achieved with antenna arrays in a very elegant way, and this will be the topic of today. All right, so let me first give you a taste, an example of what you can do with an antenna array. This is an example that fascinated me. Let me tell you what it is. So if you have, for example, a laser pointer and you want to steer the direction of the beam, you can basically just move the laser pointer around, and by that, in that simple way, change the direction at which the beam is pointing. However, if your beam is, for example, this produced by this huge radar facility, and you want to change the direction at which the beam is pointing, you cannot actually easily move a huge antenna. And look at the size here. This is the size of a person, and this antenna array is the size of a very high building, a tall building. So it's not actually practical to move the antenna around, but what you can do is you can steer the direction of the beam by changing the relative phase of these little elements electronically. This is the key idea of phased arrays, which I think is very cool. And before I actually show you the math, let me show you a very simple example of beam steering by changing the phase in a pond of water. So let me give you an example, simple example from water waves, which is easier to visualize than electromagnetic waves. So if, for example, we have a single droplet of water, this is like a point source, and naturally it creates an isotropic radiation pattern. So let's look at this movie. A very simple point source creates an isotropic radiation pattern. Now let's look at an array, a simple array of two droplets. So by using two droplets, we can actually achieve a directional radiation pattern. So what you see here is constructive interference in these directions and destructive interference along these black lines. So what you see is that we can achieve directionality by stacking point sources. All right, very simple. And now I want to show you how by varying the phase between the point sources, we can vary in time the direction of the beam. So now let's take these two, let's take these two droplets and drop them not at the same time, but with a phase lag, either this one before the other, or that one before the other. And what you can see here in the movie is how by changing the relative phase between the sources, we change the directionality of the radiation pattern. So let me show you. So let me run this movie again and look at the black lines that denote the directions of the nodes and see how they move around when we move the relative phase between the droplets. So you see here, this is the same movie again. If you just look at the black lines here, you can see how they move when we vary the relative phase between the sources. All right, so this is a simple visualization of a phase arrays from water waves. And now let me show you what this looks like in electromagnetism. So this is a simulation of Maxwell's equations. And what we have here along this line, we have a phased array, a line array of 15 point sources. And by changing the relative phase between these sources, so each source emits with a progressive phase, and I'll show you the math soon, but by varying this phase, we can vary the direction of maximum intensity of this beam. So this is a way so we can vary phases electronically, and this is a very practical way to steer the beam of antenna arrays, which is used in practice. All right, so let's make a few more introductory comments, and here they are. So one thing is that it is many times it is convenient to use identical elements to form the array, and the math becomes pretty simple. And this is what we will do in this class. Okay, we will assume that all the elements in the array are of the same form, say dipole antennas or an array of loop antennas, et cetera, but they are identical. This will be an assumption. Another assumption that we will make is that the fields of each one of the elements, the fields produced by each one of the elements add up linearly. So we neglect coupling between the elements. This is an assumption. It's not actually true. I mean, proximity effects vary the fields, but we will neglect those. And you will see that we still get very good approximation to what to the radiation patterns actually produced by antenna arrays. Third comment, which we have already seen, is that the array radiation pattern is formed by constructive and destructive interference of the waves produced by the individual sources. Okay, so what you will see is how by varying the array, we vary the radiation pattern. And I wanted to list the 5 knobs we can control about the array. So one, we can change the geometrical configuration of the array. So we can have a line array, a circular array, a rectangular or a spherical array. And I will show you examples of all of those. We can change the relative displacement between the elements, or the excitation amplitude of each one of the sources, the excitation phase, as you've seen in the movie about the water waves. By varying the phase, we will vary the angle, and we can change the relative pattern of the individual elements by choosing different elements, like a loop or a helix, et cetera, et cetera. All right, so let me conclude the introduction by giving 3 examples of antenna arrays. There are many examples, but here are 3. So this sectoral array is sometimes something you probably see when you drive in your car and you pass through a mobile communication tower. You will see this triangular structure. It's actually an array composed of 12 dipole antennas. So you have here 4 antennas on each side of this triangle. This is a sectoral array. Another very common type of an array is a Yagi-Uda array. You usually see it tilted and rotated at 90 degrees. So you see it on very old antennas on rooftops, mainly used for TV and amateur radio applications. And another example, what you see here is a phased array from a radar antenna. Here it's a NASA satellite. Very impressive picture. So antenna arrays are found everywhere, and you can find many examples. Okay, so that's all for the introduction, and let's now get into the mathematical description, and we will begin with discussing linear array antenna arrays, so a line of sources. And the main thing we will see first is how by controlling the relative phase between the antennas, we determine the direction in which the antenna emits.